My guest today is Professor Keith Riles, who is Professor of Physics at the University of Michigan. He carries out research into the fundamental forces of nature, working in both gravitational wave and elementary particle physics. Welcome, Keith.
Thank you.
Yeah, so thanks for doing this. So you have a paper, All-Sky Search for Continuous Gravitational Waves from Isolated Neutron Stars in the LIGO data. You say the report on all-sky search for continuous gravitational waves in the frequency band of 20 to 2000 hertz. Such a signal could be produced by a nearby spinning and slightly non-axisymmetric isolated neutron star in our galaxy. This search uses the LIGO data for the first 6 months of advanced LIGO's and advanced Virgo's third observational run. So before we get the details, Keith, I want to sort of set the context for gravitational waves. So Einstein's general theory of relativity put gravity in a sort of a different footing, if I understand this correctly. Gravity seems like it's a property of geometry. Is that the way to think about it?
Yeah, that's a fine way to think about it. Isaac Newton had the viewpoint of forces acting on objects, and he was quite troubled by the notion that gravity seemed to be a force at a distance. In fact, he called the whole notion absurd. But like any good physicist who doesn't understand a theoretical issue, he just shoved it under the rug and went ahead and did his calculations anyway. And he did very successful calculations, as did his successors for a couple of hundred years or so. But quite a number of physicists worried about this issue, and mathematicians too, because in the Newtonian model, for example, if the sun were to explode into, say, two pieces, one going north, so to speak, and the other one going south, normal or perpendicular to the orbital plane of the Earth, in the Newtonian framework, we would know that instantly. Somehow gravity would be transmitted to us instantaneously. And that doesn't really make any sense. And Newton realized that it didn't make any sense. But it took Einstein to realize that that there was a different way to think about this whole process. And it involves gravitational signals traveling at the speed of light. So there is a finite delay. In reality, if the sun exploded, it would take 8 minutes for us to find that out. And so we would see it both gravitationally and with light. The light would be more a dramatic issue. The way Einstein thought about it was that not that there's this force that's being exerted by one object on the other, but that each object is warping the space around it. And the sun is warping the space in a dramatic way, and the Earth also warps the space around it, but less dramatically. And so the Earth is traveling through space constrained by the warp created by the sun. And there's a famous analogy where you have a mesh cloth and you have an object that sits in it and weighs it down, makes a dimple, and other objects that roll nearby naturally respond to that dimple. It's a two-dimensional analog to what is happening, we think, in three-dimensional space. And as you may know, one really thinks of space-time as a four-dimensional kind of a network or grid or fabric. The notion that gravity is really a warping of space itself by mass is consistent with the notion that you can generate gravitational waves by shaking masses. So if you're making masses oscillate, or you're making them go around each other, and the canonical examples for us are black holes and neutron stars that are going around in binary systems, but very tight compared to, say, the Earth-Sun binary system. In that kind of a fairly extreme relativistic system where objects that are very, very heavy are traveling at significant fractions of the speed of light, then there is a tremendous swirling of space. So it goes beyond warping. It's a very dynamic swirling. And those gravitational waves that get created locally around that binary can then travel out to distant reaches of the universe. And of course, they become ripples by the time they reach us, say, even though they may have been relatively large when they began. But nonetheless, if you have a sensitive enough detector, you can see that tiny little ripple. And so the detections that we've made so far with LIGO and Virgo have been of such objects, such systems, I should say, where we've had two very large but dense compact objects merging with each other and creating transient gravitational waves that have lasted from very small fractions of a second to as much as a minute and a half in terms of the length of the signal that we can detect with the LIGO and the Virgo detectors. Yeah, go ahead.
So as you were saying, Keith, so if an extraterrestrial were to take the sun away, it will take 8 minutes before all hell breaks loose for us, right? Both in terms of light and gravitation. Earth will continue for about 8 minutes as if the sun is there, right? So it will take the gravitational effects of just eliminating the sun. It takes about 8 minutes to reach us. Is that?
Yes.
Okay. And so, so gravitational waves, as we're talking, so I want to sort of go into LIGO and Virgo in a little bit more detail. So the idea is not new, right? I think, I mean, the idea of gravitational waves came out of Einstein's theory itself, right? We had known such things existed for about 100 years now.
Yeah, so Einstein predicted gravitational waves not long after he released his general theory of relativity. I don't think it was completely unique in that prior to him, there had been other theorists who thought about the possibility that there was a gravity analog to electromagnetic waves that Maxwell had worked out in the 19th century. But it was Einstein who first really quantified it and actually made a prediction that was essentially correct. I mean, there were some errors in his early papers, but he had the basic idea correct. Although I should say that in later years, he started having second thoughts that perhaps gravitational waves were just a mathematical artifact. It wasn't really until the late 1950s that there came to be a consensus that gravitational waves really ought to exist, and that they were not just mathematical artifacts of a very complicated mathematical theory.
Yeah, so just like the cosmological constant, Einstein's errors always turn out to be good things.
Well, this is a different type of error. I mean, you know, the cosmological constant, that's a famous blunder that actually was not a blunder, but there were some, you know, relatively minor mathematical errors in his first paper.
Yeah, so I mean, LIGO I mean, we had a little bit of a discussion on LIGO before. It's a marvelous engineering accomplishment. And so I want to talk about the engineering of LIGO a little bit, and ultimately I want to get to what you're focused on, which is a little different from what LIGO has found so far, but looking at something slightly different. So LIGO is essentially a way for us to detect this huge gravitational events, maybe merging of black holes, merging of neutron stars or whatever, that sort of spins the space-time around, and it creates ripples that ultimately reaches us. I had one conceptual question, Keith. I don't know much about this. So when we think about the space-time, three space dimensions and the time dimension, when we think about curvature, does a time curvature different, or does a time curve differently from space?
I wouldn't view it as being different. I mean, even in special relativity, space and time are all tangled up with each other. You know, what you see depends on the velocity with which you're traveling, and general relativity just makes it even more complicated. When we're analyzing the response, let's say the expected response of a gravitational wave detector to a gravitational wave, we typically think in terms of a clean decoupling of space and time. We typically model that as a wave arrives in time and travels through the detector, and we detect it through what in some sense are like forces acting on the mirrors, although that's not really what's going on. But when you have to do a very detailed calculation that involves somewhat higher frequencies than the ones we've been detecting signals at so far, then you really have to take time into account a little bit more carefully. One uses a tensor analysis to work out the details, and they start to matter at higher frequencies. So, as I said, time and space are tangled up with each other.
So you can essentially decouple them in many cases. So going to LIGO, the idea, it took about 20, 30 years for it to materialize, but it has been going on for a while, right? I mean, it's a beautiful engineering feat from any angle, right? So do you want to talk a bit about what LIGO and Virgo are?
So the detectors are based on the idea of a Michelson interferometer. So some of your listeners may be familiar with the Michelson-Morley experiment, which was used, well, it was pre-Einstein, but it provided the evidence for special relativity, the independence of the speed of light with your reference frame. And the basic idea is that you have a source of light, you split it with what's called a beam splitter. And it's much easier to do that now than it was in Michelson and Morley's day. And we have lasers instead of natural light to work with. But the basic idea is you split the light into two different directions at right angles to each other. One light beam goes down one arm, what's called the interferometer, and hits a mirror and comes back. And then the other light beam going the right angle direction, and you can call these naturally x-axes and y-axes. So light that goes along the y-arm hits another mirror, comes back. And those two light beams come back together at the beam splitter, where they recombine, and you get what's known as interference. And that can be constructive or destructive interference, depending on the how the crest and the troughs of the returning beams line up with each other. And so the light that comes back to the beam splitter, some of that may go back to your light source, for us a laser, and some of it will go off at a right angle to where our light detector, our photodetector, would be located. And the way you normally operate these interferometers is to arrange the position of the beam splitter such that the two beams coming back from the X arm and the Y arm exactly or almost exactly cancel each other in terms of light that goes to your photodetector. So normally your photodetector just isn't seeing much light at all. It's not quite completely dark, but it's pretty close to that. And so when a gravitational wave comes along and very slightly changes the lengths of the X arm and the Y arm with respect to each other, which is a natural consequence of the way gravitational waves operate. They have this kind of what's called a quadrupolar nature to them, where they stretch in one direction while compressing in the other. And so the effect of the gravitational wave is to lengthen one arm while shortening the other, and then a bit later it'll reverse the roles of which one's stretching and which one's compressing. So that introduces an oscillation. And because you are disturbing this very precise cancellation that you'd arranged initially, you see an oscillation of the amount of light at the photodetector. And so that's our characteristic signal fundamentally, as we look for a flickering of light at a photodetector with a characteristic waveform that you would expect from a gravitational wave signal. That's the essence of it. And I've said beam splitters and mirrors, but in reality there are many, many mirrors, and each arm is itself what's known as a Fabry-Perot optical cavity, which is basically a resonant cavity where the light actually travels back and forth many, many times before it comes back to the beam splitter. And the reason for that is that if you make the light travel back and forth many times over this 4 kilometer long length of the arm, then during that time, the light is sensing the change, excuse me, sensing the change in the lengths of the X arm and the Y arm, and it just has more time to build up its sensitivity to that change. Every time it goes back and forth, you get a larger difference between the longer arm and the shorter arm.
Yes. So you have two arms, 4 kilometers long, perpendicular to each other. And so as I explained, the light splitter, if one arm is slightly longer than the other, when light comes back, you get some interference pattern that you can recognize. But if you let the light go back and forth many times in one arm, it has to be within that frequency domain, right? Otherwise, would we get confused? In other words, if things are getting longer on one side and then shorter later based on the frequency, if the light is moving around, wouldn't that create an issue?
Yeah, if you were talking about very large effects, you might worry about that. But we're talking about amplitudes that amount to 1 part in 10 to the 21 in terms of the actual strains, as we call them, the relative difference in the arm lengths. So the coherence of the light between the X arm and the Y arm is very well maintained, and the light bounces back and forth in both arms by the same amount. So conceptually, you can think of it as it being a difference between the two arms, but when you ask what is the size of that difference, it is tiny, tiny. And so there's no danger of losing the coherence between the X arm and the Y arm light.
So you can run some algorithms to just sort of tease that out in any case, right? So we created multiple LIGOs, right? So I know that there are 2 in the US. There was 1 in Italy, and then we went to this what's called advanced LIGO and advanced Virgo. So what's the difference there?
Yeah, so there was a period called initial LIGO, which was from roughly 2001 to 2010, and there were actually 3 LIGO interferometers running at that time. There was 1 in Livingston, Louisiana, and then 3,000 kilometers away, there were 2 in Hanford, Washington. One of the 2 in Hanford, Washington was only half the length of the other. It was a 2-kilometer interferometer. The idea was that if we saw a real detection, then we should see a different signal in the 2-kilometer versus the 4-kilometer in terms of absolute displacement, but we should see the same relative strain. It was thought that that would be a nice confirmation that we were seeing a real signal of gravitational waves. In hindsight, that was not a great idea. It just meant that we gave up twice our sensitivity for that 1 interferometer. And so there were many times when we sort of kicked ourselves for having made that choice. Now, advanced LIGO began construction at the end of that period, around 2010. And the initial plan was once again to have 2 interferometers in Washington and 1 in Louisiana, but this time to make both interferometers in Washington 4 kilometers long. But that was the plan initially, but by the time it came time to actually start construction, there had been a proposal initially from Australian colleagues to build a LIGO interferometer in Australia using the extra interferometer from Hanford. And there's a huge advantage to doing it there as opposed to in Washington, because much of our directionality for understanding where sources are located is based on timing differences. And so we don't get any benefit whatsoever from 2 interferometers in exactly the same place. There is no time difference between them. So having an interferometer somewhere else in the world is quite beneficial. So that was the original idea, but then the Australian plan fizzled because the Australian government wasn't willing to pay for it. And there's a very strong radio astronomy community in Australia, and the government decided to spend its scientific resources on something called the Square Kilometer Array, which is a fabulous project, which I hope goes forward. But the Australian government didn't go for it. But in the meantime, the Indian government stepped up, and they said they were interested. It took several years of negotiations, and it really didn't all come together until we actually had a discovery announced in 2016. But at that point, the government said, yes, we're going to go ahead with this. And LIGO India is something that will exist in the future. Construction is underway now. Civil engineering type of construction is going on right now in India. So I'm afraid that was kind of a digression in terms of what you asked.
There was 1 in Italy, I thought.
Yeah, that's right. So let me come back to that. So there are 2 other major interferometers in Europe. There's an old one called GEO in Germany, which was built by a German-UK collaboration. And they are in some sense part of LIGO. They joined the LIGO scientific collaboration, literally decades ago. And so they've been wrapped up into our scientific program all along. The GEO interferometer is not nearly as sensitive as LIGO or Virgo, but it is potentially sensitive enough that if a supernova went off in our galaxy, it might be able to detect it. And so GEO runs in what's called an astrowatch mode, where when the other interferometers are down for commissioning or for upgrades as they are now, GEO tries to run as much as it can just in case something interesting happens in our own galaxy that they might catch.
Something really big blows up. You don't want to miss it.
They might be able to catch it, so it's definitely worth a try. Now, the other interferometer in Europe, called Virgo, is comparable in sensitivity to LIGO. It's not as sensitive, but it's within a factor of 2 now, roughly. And that makes it very useful. When we have a signal detection that is seen by Virgo, then we get this other point on the globe that gives us a timing signal. And also because the Virgo interferometer is lined up in a different way compared to the alignment of the arms of the LIGO interferometers, we also get additional information on different gravitational wave polarizations, at least in principle. So it's very nice when we get a detection that all 3 interferometers see. It just allows us to extract more science, more information about the source. And so Virgo ran with initial LIGO, and I guess it was called initial Virgo, for about the same period of time. And then they shut down when we shut down and started their upgrade. And LIGO came back online as advanced LIGO in mid-2015, and we had our first data run in September 2015 and saw our first event almost immediately, extraordinarily lucky. Virgo was not ready at that point to start collecting data with their advanced Virgo sensitivity, but they were able to join us for our next run, the second observing run, in August of 2017, toward the end of that run, and they were fortunate enough to catch some detections in that last few weeks of the second run.
Yeah, so I didn't realize. So the first detection, the famous detection that we had, was all Washington, Louisiana.
Yeah, just the 2. Yeah, so
there was no confirmation. There was no confirmation from Italy on that detection.
That's correct.
So, so I want to get to your research now. So lot have been written, lot have been published about the black hole merger creating gravitational waves and the detection of it by sheer chance. Something that happened billions of years. We just turned the machine on, and a few weeks later we find it. But then I can understand this conceptually, Keith. Let me know if I'm thinking about this correctly. So if I think about a pond, and I have something in the middle of the pond that is spinning continuously, I can see this wave sort of continuous. It's sort of moving away from that spinning object. So it is possible that we have spinning neutron stars or spinning other objects that creates this continuous waves, right? It's not like a one-time event, like 2 neutron stars or 2 black holes merging, but something continuously spinning and creating this waves. So I want to understand the frequency regime here. So when we think about this, the one that we identified, the 2 black holes merging, what was the frequency regime that we were in at that time?
So that one peaked at around 250 hertz, if I remember correctly. And it was seen up until that frequency. One of the benefits of advanced LIGO was the improvement of the noise levels, the sensitivity of the detector at low frequencies. There's a dramatic improvement that came about because of a whole new suspension system for the mirrors. They hang as pendula in order to isolate them from ground motion. And by using a quadruple pendulum system and an active isolation system, the noise levels at frequencies below about 60 hertz were dramatically reduced for advanced LIGO compared to initial LIGO. And that meant that we could see the signal as it evolved through more of the band than we could have with initial LIGO. as the two black holes come together, the frequency of the orbit increases steadily in this kind of a chirp fashion. And in that particular case, when the two black holes merge together, when their short shield radii basically touched in some sense, then they were at about 250 hertz, if my memory serves me correctly. And that's a pretty good spot for our detectors. That's one of the most sensitive regions of our detectors, is sort of that 200 hertz, 300 hertz range.
So the more massive the objects are that are merging, the lower the frequency is?
Well, the lower the frequency at which they come together, because the more massive the object is, the larger the radius of the Schwarzschild, of the horizon of the black hole. It basically scales linearly. That radius is directly proportional to the mass of the system. And those two black holes were massive, roughly 30 solar masses each. In the case of two neutron stars coming together, where you have masses of more like 1.5 solar masses, they can get much closer to each other before they collide, and that allows them to go to higher frequencies and still be detectable in our band.
So higher frequency. So going back to advanced LIGO and advanced Virgo, is it easier to detect lower frequency or higher frequency?
Well, the frequencies to which we're most sensitive are around 200 hertz with advanced LIGO. And it's a pretty broad band, 200 plus or minus 100 roughly is relatively flat. And then it gets worse as you go to higher frequencies, and it gets worse again as you go to lower frequencies because of ground motion contamination and also other thermal effects in the mirrors and the suspensions.
So the neutron star mergers or neutron star, singular neutron star spinning is at a higher frequency typically?
Oh, well, it varies enormously. So a neutron star, most of the known neutron stars that we have been able to detect have been detected as pulsars, typically radio pulsars, in some cases X-ray or gamma ray or even optical pulsars. Most of them are radio pulsars. And some of the frequencies are quite low, well below a hertz. You can have periods of these periods of these spins that are 20 seconds. And that's true of most of them. We're getting close to 3,000 known pulsars, and the vast majority of them have frequencies that are outside of the LIGO Virgo band. They are below, say, 10 hertz. Nonetheless, there are hundreds that are still potentially detectable. The highest known frequency is 716 hertz for a pulsar. We would expect a gravitational wave signal to be twice that value, just from the particular quadrupolar nature of gravitational waves. We would expect that one to be about 1432 hertz in our detector. And so when we carry out searches, we go up that high and actually sometimes go even higher. The paper that you mentioned earlier goes up to 2,000 hertz, and the idea there is to just keep our eyes open. Nature might surprise us, and maybe there are rapidly spinning neutron stars that go up above 700 hertz. Maybe they go as high as 1,000 hertz. We just don't know.
So the higher the frequency, the faster the neutron star is spinning?
Yeah, that's the idea, is that the gravitational wave frequency is, at least in the simplest model, is exactly twice the rotational frequency of the star.
And so for just for my own understanding, so if you have a 50 hertz neutron star object, what's the wavelength of the gravitational waves you're talking about there, approximately?
So if it are 50 hertz, then you give 100 hertz gravitational wave. And so because the speed of gravity is the same as the speed of light, you would get the same wavelength that you would for a 100 hertz electromagnetic wave. So you're talking order 3 million kilometers. So it's a huge wavelength. We're very much in what's called the long wavelength limit in our detections.
Yeah, it's just mind-boggling. So I just want to get a good definition of neutron stars. So these are compact objects. They're not compact enough to become a black hole, I would think, right? So, but they are real objects.
They're very close.
Very close.
They're within a factor of a few of becoming black holes. They've compactified that much.
But they're real objects in the sense that you can actually see them
Yeah,
as objects.
that's
And
correct.
so when there's a real object there and it's spinning and creating gravitational waves, I didn't understand this, Keith. I read something like there could be bumps on this object, like a
Yep,
few centimeters.
we need bumps. If we want to see gravitational waves, we need bumps. Yeah, so if you have a a neutron star that is perfectly spherical, which would be the case if we were simply sitting there and having sat there for hundreds of millions of years and has slowly annealed out whatever perturbations might have been there initially. If it's just sitting there and it's not spinning, it'll be spherical. If it's spinning, it'll be an oblate spheroid. So it'll be slightly fatter at the equator than it is at the poles, just like the Earth is, but to a much smaller degree. But that kind of a bulge is not the right kind to give us gravitational waves. What we need is a non-axis symmetry about the rotation axis, about the spin axis. Going back to this notion of swirling space, if you had, say, a ball sitting out in your pond and it's just spinning, and it's a perfectly smooth ball, it doesn't actually disturb the water around it very much at all. But if that ball had a little bit of a bump on it, so that bump is going around and around and keeps disturbing the water around it, then that will create ripples. And that's the analog to what we're looking for. We need some kind of a non-axis symmetry on the star. And it doesn't have to be very large. We quantify these non-axis symmetries by what's known as the ellipticity, which is defined to be the relative difference in what's known as the moment of inertia of the star about the axes aligned in the equatorial plane with the polar plane. Well, it's really the difference between, say, the x and the y moments of inertia, where z is defined to be the spin axis. So you take the normalized difference, which is the difference between those moments of inertia divided by the average, and that's a number that we expect could theoretically be as large as 10 to the minus 6 or even 10 to the minus 5, depending on the unknown properties, what's known as the equation of state of neutron stars. But in practice, we don't know how large it actually gets. You can say theoretically, excuse me, let me drink something.
Sure.
You can say theoretically it could be as large as this value that's allowed by in some sense, the nuclear physics of the neutron star. But what it actually will be will depend on its own history. And it could well be that even if perturbations were there when the star was born in this very violent process, those perturbations, those bumps, may have just sort of ironed themselves out over the course of its lifetime. And so that's something we don't have a good handle on, is what is a plausible value for that ellipticity. We know in some cases that ellipticity has to be smaller than something like 10 to the minus 9 in some very, very old stars, for which we have the best indirect measurements based on basically observing their frequency evolution, which would be affected by a gravitational wave emission. So by seeing that the frequency is not decreasing faster than a certain rate, we can say that, well, there can't be gravitational wave emission higher than a certain level, and that implies an ellipticity, no larger than a certain value, which can be quite small for these very high frequency pulsars. So we're pushing down, but we don't know how far we have to push down.
Yeah. So it's not a local imperfection on the neutron star, so to speak, right? The longer the neutron star exists, the lower the chance of that imperfection to exist?
You expect a certain amount of annealing of a star like this. That said, there are processes that can prevent that annealing from happening too quickly. The star is emitting electromagnetic radiation to some degree. It has almost all of them that we know of have magnetic fields that are significant. And by significant, I mean giant compared to what we have here on the Earth. And the fact that they're spinning around with these strong magnetic fields means that they do emit electromagnetic radiation. And in fact, the fact that we see them as pulsars is one measure of that in many cases. So that's a process that will slow the star down. And a star that is spinning around very fast, as I mentioned earlier, is oblate. It has a certain shape to it. If it's slowing down, the equilibrium shape has to change. But the crust of a neutron star, we think, is rigid. And so we have pretty strong evidence from various processes, basically radio burst and gamma ray burst and what have you, that neutron stars have these nasty glitches that we think correspond to sudden shifts of the crust. And there are various models try to explain what's going on in detail, but the essence of it is that you have a star that's spinning down, its shape has to adjust to a new equilibrium, but it's a rigid crust. And so that means things are changing in the star, and you could imagine that there could be some perturbations. Another issue that comes into play is that we have very strong external magnetic fields we know from various measurements of known pulsars and other neutron stars. There's a strong suspicion that there are even stronger magnetic fields buried within the crust of the neutron star that have not yet, in some sense, reemerged. And if that's true, that means that there's going to be a fair amount of pent-up energy in those magnetic fields. And we know that that has to exist at some degree because things called magnetars show evidence of magnetic bursts that are analogous to, but far more violent than what happens in our sun, that gives rise to solar flares. So there's some reason to think that there are pent-up, buried, extremely strong magnetic fields inside the neutron star, and they are not necessarily going to be axisymmetric. They may themselves have all sorts of random variations in them that could lead to effectively a ellipticity that's associated with the energy of the magnetic field. One of Einstein's insights was that energy is equivalent to mass. Well, if you have this fluctuation energy distribution within the star, that in some sense corresponds to a fluctuation in mass, which leads to the kind of non-axisymmetry that I quantified in terms of moments of inertia earlier.
Yeah, I mean, it's a battle, it sounds to me, Keith, without knowing anything about it, it's a battle between gravity and electromagnetism in a spinning neutron star with a hard crust, with a sea of neutrons inside. And it sounds like a pimple forming, in some sense to make things work. But it seems counterintuitive mathematically, though. So what's the intuition behind these pimples, so to speak?
Oh, well, actually, I don't think of them that way. We often use the terminology of a bump on the surface, but a more accurate way to think about it, I think, would be, in the best case scenario, would be a bulge. So it's not just some very highly localized bump. It's more like we have a distortion that is reaching around a significant fraction of the circumference of the star. And of course, if you had a crack, literally a crack due to, for example, an escaping magnetic field or a sudden shift due to this spinning down process, it will take some time for that crack to anneal. And that crack may be, a significant fraction of the radius, say, of the star. So
it's sort of a shape deformation from a symmetry perspective, slightly deformed. And so when the deformed object spins, we can anticipate some gravitational waves and we can predict what those things might look like. Is that what you're thinking?
Yeah. The shape of the signal is actually one of the nice features. Is it's a very predictable shape. It's basically a sine wave. If we have this bulge on the surface, or something buried inside that is non-axisymmetric, then it will create, to a very good approximation, a sine wave. It'll be a sine wave that has a very gradual decrease in its frequency. So there's that tiny little bit of what's called spin down. But in the reference frame of the star, it's a very simple signal. Unfortunately, when we detect it, it's not so simple, because we're sitting on an Earth that is spinning around its axis once a day and is going around the sun once a year. And you might think those are pretty small effects, but they're actually quite significant when you're looking for unknown sources everywhere in the sky. It's not a big deal if you're looking for gravitational waves from a known pulsar and you're trying to track what that signal should look like, and we do those kinds of searches within the collaboration. But if you don't know a priori what the frequency evolution is, because you don't have radio astronomy measurements to base your search on, if you're just looking for all possibilities, then you have to assume every point in the sky is a potential source. And unfortunately, every point in the sky has a slightly different modulation with respect to the other points in the sky, because the Doppler effects depend on the direction of the source relative to the direction of the Earth's motion instantaneously. And so we have to take into account those modulations very explicitly. So the all-sky search, the subject of this paper, involves having to look over all these different possible locations in the sky and all these different frequencies, and also looking for different assumed intrinsic spin downs of the signal, because we do expect some intrinsic spin down if it's emitting gravitational radiation and may potentially also be emitting electromagnetic radiation.
So when you say all sky search, so you're not really just focused on the Milky Way. It could be pretty much anywhere.
Well, we are in the sense that we don't expect to see any signals beyond the Milky Way because we just don't have the sensitivity. But we're not looking, for example, just in the plane of the Milky Way. If we're lucky, there might be a relatively nearby neutron star that we just don't know about, floating by in our galactic neighborhood. And because it's not a pulsar with a beam that happens to point toward the Earth, it might be something that has escaped detection so far. And so, we're always hopeful that there might be something close to us, in which case we should be looking in all directions in the sky. If we were prejudiced into thinking that we have to look very far away just to get the statistics to find a source that's likely, then we would tend to look in the Milky Way plane. And researchers in this field kind of argue about these issues about, well, what's the optimum way to go about this? Should we focus on the plane or not? And it depends on how far away you think you could see a signal. And that depends on the frequency at which you're looking.
Yeah, so do we have a handle on sort of how many neutron stars are there per unit volume in the universe?
Not a strong handle, but theoretical prejudice would be that the Milky Way altogether, the galaxy altogether, has something in the ballpark of 100 million to 1 billion neutron stars, most of which would not be detectable because they were born hundreds of millions or billions of years ago, and there's no way that they still have enough spin and non-axisymmetry in them that we could see them. And so it's a very tiny fraction that are visible as pulsars, for example. As I said, we have less than the 3,000 that are known, and then there are relatively small numbers of other neutron stars that we detect in other ways electromagnetically. So if you ask how many of these neutron stars are potentially detectable within, say, a kiloparsec of the Earth, well, we don't know the answer because we don't know, again, what the ellipticity should be. But there are neutron stars, within a kiloparsec, and we think we have sensitivity to potentially interesting ellipticities within a kiloparsec. But the precise numbers are still very uncertain theoretically.
Yeah, I mean, I was just wondering, I don't think this is the case, but there was some hypothesis that the primordial black holes could be an explanation for the dark matter puzzle. Mm-hmm. Do you think if our sensitivity increases and we have a much higher confidence in sort of neutron star per unit volume. This could be one of the explanations for dark matter. I don't think so, but I just asked the question.
Yeah, well, that was well, until the first LIGO detection came along, the idea that primordial black holes explain dark matter had really fallen into theoretical disfavor because it just seemed, most of the places where you might think that would happen in terms of mass range just didn't agree with observations. But it was realized after the first detection that, well, maybe there is a loophole, that if you had for some reason, a peak in the black hole mass distribution around 30 solar masses, then perhaps that would not be at odds with other measurements of dark matter. It always seemed a little too good to be true. One reason that got some traction at the time was that many people did not expect that our first detection would be something as massive as 230 solar mass black holes. But there were some who actually did expect something like that. I mean, for example, Kip Thorne, he was expecting it to be a pretty massive black hole we saw first, not neutron stars, although we always talked about neutron stars. His expectation, and that of many other well-informed theorists, was that black holes would be more likely. And the reason for that is not that they come together that much more often per unit volume in the universe, per unit time. Is that we can see much further out when we're looking at sources that are massive, because to the first order, pretty good approximations to say that the strength of the gravitational wave is directly proportional to the mass. And so if you can see something much further out, then you are sampling a much larger volume of the universe when you look for signals of that type. And so there's a very strong selection bias in our detections that favors seeing massive black holes a long way away, even though there may be many more neutron stars merging per unit volume, per unit time. Within that volume, we can't see most of them because they're just too weak. Their characteristic mass scale is 1.4 solar masses, not 30 solar masses. So you might ask, well, what about lighter black holes? And now, we have many more detections now, and we do see lighter black holes. And in fact, the distribution tends to peak at lower values. So now that we're starting to see this more full range of the black hole mass distribution, it's becoming much less anomalous that we had this one detection at 30 on 30. That turns out to be an outlier, but it was an outlier that it's not all that surprising we saw early, because we can see it more easily than we can see lighter black hole systems. So personally, I don't think that binary black holes or black holes in general that are primordial constitute much fraction of the dark energy. We'll know in about 15 or so years, maybe a little bit more than that, ideally when we have third generation gravitational wave detectors that can actually see back so far back in time that they could see such mergers from black holes that could not yet have formed in the age of the universe, because it's going back far enough in time that no stars have formed yet. The gases have not condensed to form stars yet. And so if you see black holes that far back in time, then you can say, well, those must be primordial black holes. We'll see.
Well, there could be some sort of aggregate measurement. I'm thinking a continuous LIGO that is continuously measuring, all sorts of things for a period of time on all frequencies, and everything that it can do, to get some sort of a volumetric expectation of.
Yeah, but one issue is that what we see from black holes are mergers of binary systems, and that's some fraction of the total number of black holes out there, and we can't detect isolated black holes, at least if they are just conventional black holes. They are axisymmetric. Once they form, there's a very short period of time in which they shake off whatever non-axisymmetries they have, and then they become extremely smooth oblate spheroids if they're spinning. And so they are definitely not going to give us the bulges that we need to detect them as continuous waves. I mean, there is one interesting potential exception of that is if you have particular scalar or vector boson elementary particles that we don't yet know about, but which might exist. They can condense in the vicinity of black holes and form what are called boson clouds. And if you had a particle of just the right mass, it could actually condense around a black hole that's rapidly spinning and produce what essentially is a continuous wave gravitational wave signal. But it's one of these lamppost physics kinds of scenarios where things have to be just right for this to end up being detectable. Well, but for first of all, to exist, and even if it exists, it then needs to be in just the right mass range that we could detect it with gravitational wave detectors.
Yeah, I mean, this gravitational cosmology appears really, really interesting. It seems less expensive. Correct me if I'm wrong. I think the LIGO construction cost was about $200 million. In the grand scheme of things, we don't have to send humans out to repair it into space if something goes wrong. So it seems like sort of a long-term investment with high returns. Do you think LIGO-like things that we need more of LIGO? For example, your research, for instance, you're looking for something very specific. So do you need sort of a specialized LIGO for your observations?
Well, the LIGO that we have, in principle, should be pretty good. Since we don't know a priori what the most likely frequency of our detections will be, it's good to have a detector that is broadband in its sensitivity, that's sensitive in this case from roughly 20 hertz to 2000 hertz or so. We don't know where to look precisely. If we knew, you could actually design a slightly refined version of LIGO that is especially sensitive at certain frequencies. It's called narrowbanding the interferometer. And that was actually thought about quite seriously back a decade or so ago. In practice, we think it's better on the whole not to go there, at least until we have a really good source to go after. So for the time being, we use these broadband instruments. You were asking about the cost of LIGO. It's true that the initial cost of initial LIGO was in the ballpark of 200 million. But if you add to that the cost of advanced LIGO and you add to it the operational cost over the last 20 years, I think you would be looking close to $1 billion cumulative from the U.S. government. To build a third generation detector would be, beyond that. And I hesitate to give any numbers because I haven't actually dug into the projections lately, but it would certainly be beyond $1 billion to produce a new third generation detector.
Even at $1 billion, James Webb ultimately is going to cost about 20 billion with a 5-year expectation of life. And I was talking to Betty Freeman from Chicago recently, and it's a binary outcome. It's going to L2 if something bad happens. I hope nothing bad happens. It's gone.
Yeah.
Whereas when you have something on Earth, you can fix it up. So the risk return characteristics of LIGO appears to be extremely beneficial.
Well, I'd like to think so. I mean, there can be catastrophic problems with even LIGO. LIGO involves a gigantic vacuum tube, and one of the interferometers is in an earthquake-prone area. I happened to be at the observatory one time when there was an earthquake, a fairly massive earthquake in Tacoma, Washington, back in the early 2000s. And Ray Weiss, who happened to be at the observatory at the same time, as soon as he realized that there'd been an earthquake, which we could feel from the shaking of the ground, the first thing he did was go run to the vacuum system control panel to see if anything was wrong anywhere. Unfortunately, there was no problem, but his first thought was the vacuum system is absolutely critical. And you would worry about some catastrophic failure. mechanical rupture for one reason or another. The Livingston Observatory is in a hunting area. There are concrete structures protecting the beam pipe, but you might worry about a tornado. You might worry about something that would wreck the observatory. Nonetheless, even in the worst case scenario, it could be repaired more easily than you can repair a satellite in orbit. And I should mention that there was an incident at the Hanford Observatory where a vehicle actually collided with the concrete protection, the concrete enclosure over the beam pipe. So if that vehicle had actually hit that pipe at, I think it was going something like 40 miles an hour in the dark, I don't know what would have happened. Wouldn't have been good.
Yeah, I mean, fortunately, these are engineering problems. So we are pretty good at solving engineering problems, especially if we have access to it. Mm-hmm. And then there are some, we can ban guns. That may not happen for a few more years, but so to conclude on this, Keith, so you haven't found anything, but you're looking for them. Things that create this sort of a continuous gravitational waves because of slight non-axisymmetric shape of the object and its spinning. What's your sense right now? If you were to assign a probability that you'll find something the next 5 years, what do you think? Where do you think you are?
Well, Peter Salson, who was one of the pioneers in this field, said that you have to be an optimist to be a gravitational wave scientist, and that was true for decades, literally. And I'm an optimist, and so my probability calculations or estimates are not necessarily reliable. I guess you could say that I've voted with my feet, and that I've chosen to spend the bulk of my time on this particular kind of analysis. And so if I didn't think the probability of seeing something in the next 5 years was of order half or so, I would turn my efforts elsewhere. But that's just me.
Yeah, I mean, we know neutron stars exist. I guess we know there are non-axisymmetric neutron stars out there as well, right? From other theoretical or experimental evidence.
Well, there must be to some degree, because we have neutron stars in accreting systems. For example, low mass X-ray binary systems, where there's a neutron star that is being orbited by a relatively low mass star. Scorpius X1 is a canonical example. We do not see pulsations from that neutron star, but we're confident that accretion is happening on it. And so accretion is certainly a good way to deposit mass on a neutron star in a way that need not be symmetric. And so we actually spent a fair amount of our time as a collaboration looking for continuous waves from Scorpius X1. And also we just put out a paper recently looking for radiation from 20 accreting X-ray millisecond pulsars, cases where we actually do see the pulsars pulsations. And so we have a good sense of where to look in a frequency space. So yes, we know there are systems where neutron stars are being accreted upon. Presumably that does create some non-axisymmetry, but again, the theoretical modeling is quite uncertain. And if it's a very steady, slow accretion, then it wouldn't necessarily lead to a very large asymmetry. One possible scenario would be that if you have a star with a very strong magnetic field, there would tend to be an accumulation of mass near the magnetic poles of the star. And if those are tilted away from the spin axis, which they quite often are the way it is here on the Earth, then you could have a natural asymmetry of mass accumulation near those poles. And there have been a number of calculations and papers over the years looking at that scenario. But again, the theoretical uncertainties are very, very large.
Yeah, I mean, it seems like just a matter of time, because all the foundational elements we know exist. It's a question of sensitivity. It's a question of focus on frequency, focus on location, and so on. I know that there's some work going on in terms of once you get a gravitational signal, go look for that object. But if it is black holes merging, you probably don't find anything. But if it's a neutron star spinning, you can probably get other measurements, right? That might confirm it in some way.
Oh, you're asking in the case where we see a previously unknown neutron star and we want to
So
confirm.
suppose you get some sort of gravitational signal,
Yeah.
you can
So
go back and look at it, right? Yeah.
right. So if it's a known pulsar, then we're already looking for it. If it's in our band, for the most part. Um, but if we detect something in our all sky search from a point in the sky where there's no known neutron star, then what we would do is contact our friends in the radio astronomy community and the X-ray astronomy community and gamma ray astronomy community and ask them to look there. We would say, hey, here are the coordinates, and in principle, we could nail those coordinates down pretty precisely, um, better than an arc second, if we had, say, a year's worth of observations. And we could ask them to take a look there and look as deeply as they can with their instruments to see if they see, first of all, is there an object there at all in our galaxy? And if so, do they see any evidence of pulsations that match the frequency that we see?
Yeah, so this location specificity is sort of unique to this continuous measurement, right? So
Yeah.
since you're getting lot of data, you can actually pin it down where it's coming from, rather than sort of a single event and you picked up something.
Yeah. The key to it, and you can actually do this with a single detector. You don't even need triangulation from other detectors. And the reason for that is that you can think of the Earth's orbit as being the effective aperture of our telescope. We're seeing the signal today, and then we're seeing it next week, and then we're seeing it 6 months from now, and we're in a very different location in our solar system. And so in order to for that signal to even reconstruct properly, we have to assume it's coming from the right location. And if you think about a telescope whose aperture is the size of the solar system, you have very good angular resolution. Now, it's not the same resolution you would have from an optical telescope of that aperture, because our wavelengths, as we discussed earlier, are gigantic compared to visible wavelengths. So we do pay a big price there. But if you work out the numbers, it's better than an arc second of resolution from the Earth's orbit.
Yeah, so let me ask you one final question, Keith. So this gravitational sort of cosmology, do you think as engineering improves, as our measurement sensitivity improves, we might be able to pick up something from the Big Bang at some point?
Well, that's a good question. We do expect that there was some sort of gravitational radiation analog to the cosmic microwave background radiation. And we look for that. Every time we have an observing run, we look for what's known as stochastic radiation, looking for a background exactly like that. We have not yet seen anything like that. The problem we're going to run into is, in seeing that far back, is that there's another random radiation background we expect to see first. And that's going to be the superposition of all of the distant mergers of black holes and neutron stars and black holes with neutron stars. We have predictions for that are getting ever more precise as we make more measurements of the population of those mergers. And so we now have a pretty good sense that within the next 5 years, say, we're going to see that background. We're going to see a stochastic background from sources that we cannot resolve individually, but added together from very distant regions of the universe are looking like a random background. So once we're in that regime, it's going to be hard to disentangle that random pattern from a random pattern due to the Big Bang. It's not out of the question. If the Big Bang radiation were strong enough, it would have a different spectral shape to it, and we might be able to disentangle it that way, given our predictions based on known mergers. But it'll be a tricky situation. And the theoretical prejudice is to not expect the Big Bang radiation to be that strong in the first place. Standard cosmology doesn't predict very strong radiation from that time. There are other cosmological theories that do predict other kinds of background. There are cosmic strings, for example, you may have heard of, sort of defects in the universe that are in some sense whipping around and creating all kinds of random gravitational waves. And we look for that. We put out a paper on that this year. And so if that exists, that might be seen at a much higher level than you'd expect from a standard Big Bang model.
Yeah, there's a lot of noise, so you have to remove all the noise to see,
Right,
see what
there's
happens.
no noise to start with. There's the instrumental noise, the environmental noise from being on the Earth's surface, and then you have potential noise in the signals themselves.
Excellent. Yeah, this has been great, Keith. Thanks so much for spending time with me.
Well, thank you. I really enjoyed the conversation.
Thank you.
Bye. So